Here we're going to talk about numerical integration, which is a way that we can use knowledge about points in a function as opposed to having to understand much about the entire function, but rather we use sample points to estimate the value of the integral of that function. We'll talk about the motivation, specifically an example in robotics, and then we'll talk about certain formulas derived based on an idea from Newton-Cotes. Specifically talk about trapezoidal and Simpson rules. We'll talk about composite formulas, that is applying the same idea piece by piece in a function. We'll talk about errors as a function of step size, and we'll talk about MATLAB implementations. So first of all, let's start with an example. Why would this be useful, particularly useful in biomedical engineering? Here you have an example of what's called a robotic surgeon, meaning these are robotic high-precision instrumentation performing an operation, but these are being controlled by an operator sitting away from the instrument itself, attached through video observation and high-precision controls. So this person is looking at manipulating a robotic arm with extremely very fine precision in a very delicate environment where errors are to be minimized. This is done very commonly these days, in particular in brain surgery, in complicated reconstruction surgeries, as this video is showing here. Where does integration and differentiation come in this particular example? Well, these are instruments that are controlled by devices that apply forces to these scalpels and other procedures. So forces, as we're going to talk about, are mass times acceleration. They're described as that. So we need to understand which force to apply to move the tip of the instrument to what position exactly. So talking about the math involved here, we start from force equals mass times acceleration, and we understand the acceleration here. This is a vector, so this is why it's in bold font. We have that a here's acceleration vector is the derivative of the velocity vector. So we can go from the acceleration. If we have knowledge of acceleration, we can perform integration and obtain the velocity, which we integrate once more, and we can obtain the position of the device, right? So from a certain acceleration being applied to the robotic arm, we can understand where the position of that device will be at a certain time t. Of course, we can go back the other way if we take the position and differentiate with respect to time, right? So all these integrals here are with respect to time, and all these derivatives are also with respect to time. So how does numerical integration work, right? So here we have a function, f of x. The function itself is drawn here in red, and we would like to obtain the integral of this function. Oftentimes, this is hard to do by hand, because for many functions, for example, the Gaussian function, very popular in probability, we don't have an analytical form for the integral. Rather, we can estimate what the integral is by doing certain calculations, and the most popular way is to select certain sample points throughout the function. We can evaluate the function, and then we can use a simple or simpler approximation to that function that, let's say, interpolates through these sample points, and we use this, right? We can, for example, obtain an estimate of the integral around this vicinity, particularly here, by computing very quickly the integral of the area of this rectangle that fits in that region of the function. So this is more or less the gist of what we'll talk about in this presentation, specifically that we have a few goals here, which is hopefully by the end of this video you'll be able to explain how numerical integration algorithms work, understand advantages and disadvantages of the trapezoid and Simpson rules for integration, understand how the approximating function and step size affect the error, and be able to apply this to real data, as well as be cognizant of effects of data error or noise on the data that you are performing integration over. So let's look at this idea from Newton-Cotes. We start from the observation that while we may not know exactly what the integral of an entire function is, we can approximate this function by something simpler. And we've looked at how to interpolate data points using polynomials just a few videos back. So here we have a polynomial degree 1, right? So this is a line fit between 2 points. And we can estimate the area under this line very, very easily, right? Or we can take 3 points and fit a parabola here, or a quadratic function. And once we have a quadratic function, we can integrate polynomials sort of easily, right? So, and of course, we notice that if we're going to obtain an integral between a and b for this function, rather we can split this idea into many little steps, so that while you may still obtain the errors in each step, the errors, if you take a small little step, the area under this parallelogram here will be more closely matching the area of the curve under a shorter interval. Here, for example, you can see that you have a big error when you try to approximate that way. So the general idea is, instead of estimating exactly the integral from the exact function, rather we substitute this function f by something we call f subscript n. In this case would be a polynomial, and we substitute this polynomial integral, and we know how to integrate a polynomial, right? So in the example here, if we do this line, right, so the integral would essentially be the average height. So that's the gist of the idea. So let's look at a particular example. Right? Let's look at what's called the trapezoidal rule. Here we estimate that our approximating or interpolating polynomial here will be of degree 1, meaning a straight line. And once we plug in this straight line, which we can fit from the Lagrange interpolation formula that we just described a few videos back, for example, we can then integrate this line, and we get this formula here, which tells you, take f of a and f of b and compute the average here, and multiply the height by the length, and it gives you an approximation for this integral. But as you can see, this approximation will have a significant error in this specific example shown. More precisely, what is the size of this error? We're not going to do this here, but you can use some Taylor series arguments to come up with an estimate of what the total error for this integration is, right? So for example, the error can be pretty bad if you take this starting point and this is the ending point, and you apply the procedure. The error under this integral will be very large, right? This is the real integral minus that part. And in this case, the error goes as the cubic power of the interval, right, as well as the second derivative. So we can use this knowledge that the error goes as the cubic power, meaning if we make this interval smaller and smaller, right, say less than 1, something less than 1 to the cubic power will be even less, much less than 1, right? So if we reduce this integral by, instead of doing one entire approximation, we do many little approximations, we can improve this error. And this leads us to this composite integration formula. So let's say we have an integral here from a to b, but we distribute 5 equidistant points, or in this case 6, right, because you count the initial point as well included. And so we then estimate the integral from a to b, which is x0 to xn, as the sum of the integral estimates from each region, right? And we apply the same trapezoidal rule for each little region, and you can have this estimate, which you can regroup and estimate that this is going to be essentially a formula that you can apply. Actually, in fact, it's like a matrix applied to the vector of points comprised from the approximations of this integral. So it's a very simple formula to implement. So here's what the a typical MATLAB implementation looks like, right? So here's a generic way to write such a function, where you pass the function handle, you pass the left coordinate, the rightmost coordinate, and you say how many regions in between I want to use. Of course, in this case here, the default for the arguments, if you don't pass that, will be 100. So you compute the h to be 100, the h being this step size on the x-axis, and then you simply evaluate your function at these points, and you evaluate the formula given in the previous slide, and you compute the I here, which is the total sum of the integrals of all of these little regions, and that's your result. So it's a pretty straightforward formula to implement. So one drawback of the trapezoidal rule is that the error is related to the second derivative of the function. And so that means that the more complicated formulas are, we can essentially try to improve the accuracy of the curves by using second order and third order polynomials, and the results from these formulas are so-called Simpson rules. So let's look at what some of these might be, right? So here is the first famous Simpson 1/3 rule. This corresponds to using a second order polynomial where we use Lagrange interpolation to form a quadratic fit between three data points. Right now we take 3 points along our curve, and we apply the formula which we derived a little while before, and we integrate this polynomial. This is just a second degree polynomial, can be integrated, and this is the formula you end up with. The error can be similarly estimated, but now you can see that the error here is with respect to the fourth derivative of the function, and more importantly, it's also the fifth power of the interval, right? So if we reduce, let's say, to the interval to half, 0.5 to the fifth is something even much smaller than 0.5 to the third. And this is an advantage that can reduce the error of these integration formulas. Like we did for the trapezoidal rule, we can also apply these formulas region by region, right? So we can select a small region here, and we apply this 1-for-1 weights to these three, and then we apply 1-for-1 weight to these three, 1-for-1 to this. So the length of these guys here give you the 3 points that you need, and you sum all of them up, and you end up with a formula that is expressed here. The next one is we can go one up on this idea. And by the way, the 1/3 or the 3/8 have to do the coefficients that result from this interpolation and integration procedure, right? So now if we take 4 points per region, then we can fit a third order polynomial. Fn is now a third order polynomial here, and we can integrate it to obtain this formula here, where you have the 3's and the 3/8, right? So the 3/8 that come out front are related to the naming convention here. And you can expand this idea even to higher order polynomials, right? You can fit a fourth order, fifth order polynomial and integrate those formulas as well, and you can get more and more accuracy that way. You can also apply this formula with uneven segments, right? So we've split an interval in even segments or equidistant points. That does not necessarily have to be the case. So as long as you have coordinates like 0, x1, x2, x3, and so on, you can use those formulas and plug it into this general approximation formula, and it works the same. And all you have to do now is pass both the x coordinate and the y coordinate. Before, we just passed to this function the left hand side of the function and the right hand limits that we wanted to integrate over, but now if we pass x and y, this very similar formula for the trapezoidal of unequally distant nodes can be implemented. A few MATLAB functions that you might want to be familiar with that perform these things for you is called the trap-z for trapezoid, where you can pass in the data vector of sample values from your function. You will perform all these things for you. If your function is defined on not equidistant nodes, you can also pass the value of the nodes, and it will give you a more accurate estimation that way. If your x is omitted, for example, as in this case, the function assumes that the h is 1. Right. The other one that you can produce the cumulative integration. So this function here, trapezoid z, will give you back a number that is the integration over this vector that you're passing to the function. You can integrate, cumulatively up to a certain value of the function, and that's this function here. Hard to pronounce, but likewise you can pass also unequally distant points to this function as well, and you will understand what you mean. The final note that I'll make is that we learned how to apply these formulas for integrating a one-dimensional function, meaning one independent variable. Now there are many applications when you want to integrate over 2 or 3 or more independent variables, and you can apply this in a straightforward manner, just like you would integration, right? So first you integrate along the x-axis, for example, right? And here you have this formula being applied in this x-coordinate here first, and then you apply on the y-coordinate. It's a similar technique that will also give you a way to estimate multivariate integrals as well.